This is a video on work. So we've been doing calculus for a while, and you may think you've been working hard, but you don't even know the meaning of work until today. So what I'm going to talk about today is the meaning of work and how to use calculus to find work. So we'll start out with the definition of work, and we'll have lots of applications. We're going to be looking at the Hooke's law. Hooke's law is going to tell us how much force there will be on a spring if you're a certain distance from equilibrium. And then we'll look at rockets. Let's find out how much work it takes to go to space. And then we'll look at tanks. So we're going to look at tanks that are filled with liquid, maybe water. And we're going to empty a tank and find out how much work that takes. And then we'll look at chains. So if we have something that is connected to a chain and we want to lift it up using that chain, how much work will it take? And then finally, we'll look at cars. And in particular, we're going to be looking at pistons and see how much work is gained by making a piston happen or compressing a piston. So let's start out with the definition of work. The idea is we want to find out how much work it takes to move something. So first thing, to move something, there's going to be a force that you're moving against. So for example, you may be moving against the force of gravity, or you might be moving against some kind of pressure force. There's lots of different forces you can move against. So in particular, the work is going to be equal to the force exerted on that object times the distance that you're trying to move the object. So in terms of the units, F will stand for force, and S will stand for distance. Sometimes we'll use X if it's a horizontal distance, or Y if it's a vertical distance, whatever's convenient. I don't like to use D because D is reserved for derivatives, so let's stay away from D. So here's an example, very simple example. You want to throw a 2-kilogram ball up 3 meters. How much work will it take? So the first thing to note is that kilograms are not units of force. Kilograms are units of mass. So you have to realize that the force is equal to the mass times the acceleration. And since we're in standard units, scientific units, the mass was 2 kilograms, and the acceleration was 9.8 meters per second squared. And if you multiply 2 times 9.8, you get 19.6. So now we could put this together and find the work done. So the work done to throw a 2-kilogram ball up 3 meters will be the 19.6, that's the amount of force, times the 3 meters, that's the distance. And if I multiply that out, I get 59.88, and the units that you use for work are joules. So that was pretty easy. All you had to do was multiplication. And you know, since this is just the beginning and we have a lot more applications, we're going to be doing a lot more than multiplication. And in fact, as you might guess, we're going to be doing calculus. And in fact, the calculus we're going to do will eventually be an integral. So now let's look at a more complicated example where we have changing stuff. So let's look at Hooke's law. So if you have a spring and you want to pull that spring out, or you want to compress that spring, it's going to take force. Now, Hooke's law says that the farther you pull it out, or the more you compress it, the more force it's going to take where you happen to be. So in particular, Hooke figured out that the force needed to compress a spring x units from its equilibrium point is F equals kx. Or in other words, the force is proportional to the distance from the equilibrium point. So now that we have Hooke's law, we can use it to find work. All right, let's look at an example. You measure that it takes 4 newtons to compress a spring 0.02 meters from its equilibrium point. How much work does it take to compress it an additional 0.03 meters? So let's use Hooke's law. We have F is equal to kx. I plug in. The force was 4 newtons, so there's 4, equals k times x, which is the distance from the equilibrium point, and that's 0.02. And if I divide 4 divided by 0.02, I get 200. So now we know that our work, we're not going to look at all the work, because notice that as you're compressing that spring, you have more or less force depending on whether you're closer or farther from the equilibrium point. So in particular, let's look at the little tiny bit of work done by compressing it a tiny amount. I call that delta W. So delta W is equal to the force, which is 200, times the x, because F equals kx, and k was 200. So delta W is equal to the force, which was 200, because that's k times x, so there's 200x, times that little bit of distance I traveled, and we call that delta x. So I don't want delta W, I want the total amount of work. Well, if we know how much little work in terms of delta x, and if I want to add up all the little tiny pieces of work, then hopefully you know by now, that's an integral. So the work is going to be the integral from 0.02, because that's where I started, and I did an additional 0.03, so I'm up to 0.05, of 200x, the delta x becomes a dx. And when I integrate that, I get 0.21 joules. And that's how much work it takes to compress a spring. Okay, let's look at another example now. Let's look at rockets. So it's always fun to think about shooting yourself off into space. So let's see how much work it takes. So to do that, we're going to first use Newton's law of gravity. And what that says is that the force, the gravitational force on an object, is inversely proportional to the square of the distance from that center of mass. Or in other words, F is equal to k divided by x squared. Now, once I have a formula for F, then I can think about work done. So here's an example. How much work against gravity does it take to send a 600 Newton astronaut from sea level to an orbit that is 400,000 meters from the surface of the Earth, given that the radius of the Earth is 6,371,000 meters? So it's going to take a bit of work. Now, rocket science is actually a little bit harder than that, or maybe a whole lot harder than that. First thing is, yeah, you got to send the person, but of course there's the rocket ship. The fuel is changing, then the Earth is moving, and then of course there's air resistance, all kinds of stuff that you got to deal with. But we're just going to keep it simple, and we're just going to look at how much work we have to do against gravity for just the astronaut. So here's what we do. So first thing is I'm going to use F equals k over x squared. We know that the astronaut weighs 600 newtons. So 600, that's the force, will be k over x squared. X squared is the radius of the Earth because we're starting at sea level, which is 6,371,000 meters from the center. So I worked that out, and I get k is about 2.4 times 10 to the 16th power. Okay, when we're dealing with rocket science, you're going to deal with some big numbers, like this one. So now we just find the work. So again, what we're going to do is we're going to think about the work one little one little millimeter at a time. And then we're going to make it even smaller and smaller. I'm going to add up all those little pieces. And we're going to have the force times a little tiny distance, the delta x. Adding them up, you end up with an integral. So we're going to have the work is the integral from sea level, which is the 6,371,000 meters, to how far the astronaut's going. Well, if the astronaut's going another 400,000 meters, add 400,000 to that, and you get 6,771,000. And then we have the force, which is k over x squared, times the distance, which is our little tiny delta x, which becomes dx in the integral. And I worked that out. This is a pretty easy integral. The integral of 1 over x squared is negative 1 over x. And I plugged in our numbers. I plugged in my k. And I ended up with 226 million joules. So it's a lot of work to send a person up into space. Okay, now let's look at the next example. And that's about emptying a tank. So let's look at the problem. And it says the following. A conical tank, as shown in the figure, is to be emptied. So notice we have a conical tank. The height of this tank is 10 meters, and the radius at the top of the tank is 5 meters. What is the total work if the density of water is 1,000 kilograms per cubic meter? So to find the total work, what we're going to do is we can imagine just taking a little disc that's a cross-section of this cone, and we're going to drop that disc to the bottom and empty it out. We can think of at the bottom we might have some generator. So we're going to generate power. We're going to find out kind of how much power, how much electricity can we generate. And one of the things is work is proportional to power. And so if you know how much work, you can figure out how much power. We're just going to find out how much work. And then if you take an engineering course, you can find out how much power also. So the first thing is let's look at the volume of this tiny cross-section. Well, the volume is going to be the area of the cross-section times this little height. The little height we'll call delta y. Well, the area, circle, the area is pi r squared. So delta v is pi r squared delta y. Okay, we're going to have to find the area of this circle. We know it's pi r squared, but the question is what's r? So r is going to be the distance from here to here, from the center of the little circle to the edge. Well, at the top, we know that distance is 5, but where we are, it's not 5 anymore. So the key here is I'm going to draw a height, and then the radius, and I can use similar triangles. And what I can say is that 5 is to 10, so that's the radius is to the height, as r is to y. And then I can solve for r. 5/10, of course, is 1/2. And I get r is equal to 1/2 y. So now I can find the force. So remember, the force is equal to the mass times the acceleration, or the acceleration times the mass. The acceleration is 9.8. The mass I'll call m for now, but I need to find the mass. Well, we know that the density is 1,000 kilograms per meter cubed. So if I take the density and multiply by the volume, then I'll get the kilograms, because meters cubed is a volume unit. So I'm going to take the density, which is 1,000, and then multiply by the volume. The volume is going to be pi r squared delta y, so it's pi times 1/2 y, that's our r, squared delta y. And then I worked that out, and I got 2,450 pi y squared delta y. Now that we know the force, it's pretty easy to find the work, because the work is just going to be the integral of the force times the distance. So our force was the 2,450 pi y squared delta y. The distance is just y, because we're dropping it down y. So y squared times y is y cubed. I pulled out the 2450 pi. I'm integrating from 0 to 10, because the tank is full. Y cubed dy, and I get 19,242,255 joules. And that's how much work it takes to empty this tank, or how much work you gain by emptying the tank. Okay, let's do the next example. I'm going to call this lifting a chain, and you can look at the picture. What we have is a 1,500 kilogram car. It went off a cliff. Bad day for that car and the driver. Hopefully there's nobody in there. And that cliff is 40 meters. It will be pulled up using a chain that weighs 6 kilograms per meter. How much work will it take? The key on this problem is to break this problem up into two pieces. The first piece is just ignore the chain. Think about the car itself. If we're going to lift that car up, forget the chain, how much work does it take just for that car to be lifted up? Ignoring the chain. And that's just simple because that's just like throwing the ball in the air that we had in the very first example. And we know that we had a 1,500 kilogram car. Again, F equals MA. M is 1,500, A is 9.8. And then we have to multiply by the distance, which is 40. And we get 588,000 joules. Very simple. Work is equal to the force times the distance traveled. So it's just the force, which is 1,500 times 9.8. Distance traveled was 40, and there we have it. So now that we've found the work to lift just the car up, now let's find out the additional work it will take to lift that chain that's pulling up the car, because we got to lift that chain up too. So we're going to look at one chain link at a time, or a little delta chain, tiny bit of chain. So first thing is that the work, or delta W, will be the little bit of force to lift that little tiny bit of chain, times the distance that you have to lift that chain up to. The distance you have to lift the chain up to, let's call that y. And the little bit of force, well, F equals MA. M is 6. And A is 9.8. So we get is 6 times 9.8 times delta y. Now it's 6 kilograms per meter, but we're going to have delta y meters. So 6 kilograms per meter times delta y meters is 6 delta y. Kilograms times 9.8 to make them newtons, and then times y to make them joules. And when I multiply it, I get 58.8 y delta y. So to find out the total work, we're used to this. We add up all the little bits of work. And we take a limit as delta y goes to 0. And what do you know? We have an integral. I can pull the 58.8 outside the integral. And I get 58.8 times the integral from 0 to 40. It's a 40-meter cliff. Times just y dy. And when I integrate that, I get 47,040 joules. So finally, if I want to find out the total amount of work, I find the work for the car plus the work for the chain. I add them up, and I get 635,040 joules. And that's how much it takes, how much work it takes to lift up the car with the chain, including the work that it takes to lift the chain. Okay, another example. And that's running an automobile. So the question here is a piston has gas filled to a volume of 0.02 cubic meters and a pressure of 40,000 newtons per square meter. Find the work done by the gas in expanding the piston to 0.05 cubic meters. So if you're looking at a car that is run using gasoline, not an electric car, but a gas-powered car, that's how they work, is you get the gas fires it up, the piston gets compressed, it pulls out, and it goes back and forth, and that eventually moves the wheels. So, again, I'm not going to teach you everything about cars. In fact, I am not an auto engineer, but I know math. And I can figure this problem out because it's Simple physics, or it will be by the time you become engineers. Notice that the pressure has units, newtons per meter squared. So if I multiply by meter squared, I get newtons. So what we can say now is that the force is equal to the pressure times the area, meter squared or area. The area of a little cross section is just pi r squared, because if we cut the cylinder, we get a disk or a circle. The pressure is equal to K over V, K over the volume. And that comes from the ideal gas law, or Boyle's law, depending how you learned it. PV equals nRT, nRT called K, so P equals K over V. So now we can look at the work. So the work for that little tiny piece, to move it a little bit, is going to be the pressure times the area, because that's the force, times the distance traveled, delta x. But now note that pi r squared delta x is delta v, because the piston is cylindrically shaped, and the volume of a cylinder is pi r squared times the height. The height is delta x, so there's my little volume. Now I can put this together and say that the work now, if we add them all up, now instead of a delta x, we have a delta v, so we're going to have a dv, and we're going to integrate k over v dv from the beginning to the end, which is 0.02 to 0.05. And if I work that out, I get k times the natural log of 2.5, or 5 halves. But now I got to find k. Well, we know that 40,000 is the pressure at the beginning at 0.02 cubic meters. So 40,000 is k over 0.02. So k is 8 million. So now let's put this all together. And I can say the work is going to be k times the natural log of 2.5, or 8 million times the natural log of 2.5. And that's about 7,330,326 joules. Now I found the work to expand that piston. So we now know how to find work. We understand the definition of work. We understand how to find work in many different instances, from just throwing a ball in the air, no calculus needed, and then all of a sudden you get into Hooke's law and rocket science and lifting up a chain and emptying a tank, running an automobile. Work is one of the most important principles in physics. And if you don't understand integration, you can't do work. So now that you understand the meaning of work and how to do work, you should succeed in this course. And that is the end of this lecture. Thank you for listening.